Imagine a telescope so powerful it could peer back to the dawn of the universe, yet so hidden it's buried deep inside an asteroid. This isn't a scene from a science fiction film. It's a real, groundbreaking idea that astronomers and engineers are actively working to bring to life. For centuries, humanity has looked to the skies with wonder, building ever more advanced tools to unravel the mysteries of the cosmos. From Galileo's first crude telescope to the magnificent James Webb Space Telescope, each leap has expanded our vision. But now, we're on the verge of something even more extraordinary, something that could redefine not just how we see the universe, but how we interact with it. Think about the limitations we face today. Even our most advanced space telescopes are constrained by size, exposure to radiation, and the sheer difficulty of maintaining stability in the void. What if we could turn the natural architecture of our solar system to our advantage? What if, instead of building observatories and launching them into space, we built them within the asteroids themselves, transforming ancient, drifting rocks into the most stable, protected, and powerful eyes on the universe ever conceived? This is the promise of asteroid-based telescopes, a leap so profound it could let us witness the formation of the first stars, analyze the atmospheres of distant Earth-like planets, and even shed light on the invisible forces of dark matter and dark energy. In this video, we're going to explore why this isn't just a far-off dream but a tangible next step in cosmic exploration. We'll break down the science behind using asteroids as both shield and foundation, dive into the engineering marvels that could make it possible, and uncover the breathtaking discoveries that might be waiting just beyond our current sight. You'll come away understanding not just how we might build these cosmic observatories, but why doing so could answer some of humanity's oldest and most profound questions. So settle in and open your mind. We're about to journey into a future where the rocks floating in space become our windows to the dawn of time. But for all their breathtaking achievements, our current telescopes are pushing against some very hard limits. Think about the view from Earth first. Even from the highest mountaintop observatories, our planet's atmosphere acts like a turbulent ocean of air, constantly bending and blurring the light from distant stars and galaxies. This is why stars appear to twinkle. It's beautiful to the naked eye, but for astronomers, it's a frustrating distortion that smears fine details and limits the clarity of our deepest observations. We've developed adaptive optics to correct for this shimmering effect, but it's a constant, complex battle against nature, and it never completely eliminates the problem. Then there are the space-based telescopes like the incredible James Webb. By leaving the atmosphere behind, they avoid that particular hurdle, but they trade it for a whole new set of challenges. In the vacuum of space, they are completely exposed. They're bombarded by intense cosmic radiation that can degrade sensitive electronics over time. They face a constant, low-level sandblasting from micrometeorites, tiny particles traveling at incredible speeds that can pit mirrors and damage critical components. And perhaps most critically, they endure wild temperature swings. As they move in and out of sunlight, their metal and glass structures expand and contract, threatening the perfect nanometer-scale alignment required for their mirrors to function. Keeping Webb at its required -387 degrees Fahrenheit was a monumental engineering feat requiring a massive sun shield, and that complexity adds risk and limits design options. And underlying all of this is perhaps the most fundamental constraint of all, the rocket. Every single thing we want to put into space, no matter how large the final observatory is meant to be, must fit inside a rocket fairing and cannot weigh more than the rocket can lift. The James Webb's 18-segment mirror was a masterpiece of origami-like folding, designed to carefully unpack itself in a series of hundreds of delicate steps a million miles from Earth. But that complexity is a direct result of the launch size constraint. We are essentially trying to unravel the deepest secrets of the cosmos with instruments that must be designed around the dimensions of a rocket's payload bay. This size limit directly caps the resolution and light-gathering power we can achieve. To see further back in time, to the very first glimmers of light from the earliest stars, we need to collect the faintest whispers of photons, and that requires truly enormous mirrors, far larger than any rocket could ever hope to carry. We've reached a point where incremental improvements aren't enough. To take the next monumental leap in our understanding of the universe, we need to stop fighting the harsh environment of space and start using it to our advantage. We need to think not just about what we launch, but what we can find and use already out there, waiting for us. So instead of fighting against the harshness of space, what if we could use it? This is where the humble asteroid enters the story, not as a threat, but as a potential partner. These ancient, rocky bodies, often seen as relics of a violent past, could actually provide the perfect natural fortress for our next generation of observatories. Think of an asteroid as a ready-made cosmic bunker. Its solid, often metallic and silicate-rich exterior has been shielding its interior from the very hazards we worry about for billions of years. By carefully hollowing out a portion of one of these space rocks, we could create a cavernous, protected home for the most sensitive telescope arrays imaginable. The primary benefit is immediate and profound: radiation shielding. In the empty void, high-energy cosmic rays and solar radiation constantly bombard electronics and optics, causing gradual degradation and data corruption. An asteroid's bulk, potentially meters or even tens of meters thick, acts as a massive, natural radiation barrier, absorbing these harmful particles. It's a level of protection that would be impossibly heavy and expensive to launch from Earth. Then there's the threat of micrometeorites. While a direct hit from a large asteroid is a catastrophe, the constant peppering from tiny, sand grain-sized particles is a persistent nuisance for free-flying telescopes, slowly eroding surfaces and damaging components. Nestled inside an asteroid, the telescope would be safely tucked away, with the rock itself serving as a sacrificial shield, taking the tiny hits so the precious instruments don't have to. Beyond just physical protection, an asteroid offers a remarkable degree of thermal stability. The vacuum of space is a place of extreme temperatures, with blistering heat on sun-facing sides and frigid cold in the shadows. This constant cycling is a nightmare for Chinese letter instrumentation that requires unwavering stability. But within the heart of an asteroid, the sheer mass of rock acts as a tremendous thermal battery, smoothing out those wild swings and maintaining a much more consistent, stable temperature. This passive thermal management is a huge advantage, especially for infrared telescopes that need to be kept extremely cold to function properly. It drastically reduces the need for complex, power-hungry, and potentially failure-prone active cooling systems. This approach represents a fundamental shift in our philosophy of space exploration. For decades, we've been building exquisite but incredibly fragile machines and then expending enormous effort to keep them alive in an environment that is actively trying to destroy them. The concept of an asteroid-based telescope flips this script. It's not about building a standalone structure and then protecting it. It's about integration. It's about finding a suitable natural structure already in space and adapting it, using its inherent properties, its mass, its composition, its location, to our advantage. We stop seeing the space environment as an adversary to be overcome and start seeing it as a toolkit full of resources waiting to be used. This is the move from simply visiting space to truly learning how to live and work within it, turning a potential obstacle into our greatest asset. But protection is only half the battle. To peer into the deepest corners of the universe, a telescope needs more than just a good shield. It needs rock-solid stability. Imagine trying to take a long-exposure photograph with a camera that's constantly, ever so slightly drifting and jittering. The image would turn out as a blurry, useless mess. This is the constant struggle for space telescopes. Out in the void, there's no stable ground to anchor to. Even the most advanced reaction wheels and thruster systems are fighting a never-ending battle against tiny forces, the faint but persistent push of solar radiation, the subtle gravitational tugs from the moon and planets, even the minuscule pressure from the photons of starlight hitting the spacecraft itself. Every tiny correction burns precious fuel, and once that fuel is gone, the mission is effectively over, no matter how healthy the instruments are. It's a race against time, limiting how long these billion-dollar observatories can do their most demanding work. This is where the orbital mechanics of certain asteroids offer a truly elegant solution. Throughout our solar system, there exist special gravitational sweet spots known as Lagrange points. These are places where the combined gravitational pull of two large bodies, like the Earth and the Sun, creates a point of equilibrium. An object placed at one of these points will essentially orbit in lockstep with the planets, requiring very little energy to maintain its position. Now consider an asteroid that has naturally migrated into one of these stable zones over millions of years. It's already a perfectly balanced, naturally anchored platform. By placing our telescope inside such an asteroid, we aren't fighting physics anymore, we're harnessing it. We inherit that innate stability for free. The implications of this are enormous. First, it drastically reduces or potentially even eliminates the need for constant thruster firings. This conservation of fuel could extend the operational life of the observatory from a decade to perhaps a century, transforming it from a finite mission into a permanent fixture for discovery. More importantly, this supreme stability is the absolute key to unlocking the universe's faintest secrets. Studying the earliest galaxies or analyzing the atmospheres of distant exoplanets requires holding a telescope gaze perfectly fixed on a single, incredibly dim patch of sky for days, weeks, or even months at a time. Any movement, any vibration, no matter how tiny, smears the data and obscures the faint signals we're desperately trying to detect. An asteroid-anchored telescope, virtually motionless in its gravitational harbor, provides that perfect, unwavering gaze. It's the difference between trying to read a book while standing on a rocking boat and reading that same book while seated in a solid, anchored library. The latter allows for a level of focus and clarity that was previously unimaginable, opening a new window into the cosmos that is both steady and enduring. And that inherent stability leads us directly to another monumental advantage, one that shatters a fundamental barrier that has constrained astronomers for the entire history of space exploration: the sheer physical size of our instruments. For decades, the ultimate cap on a telescope's power has been dictated not by our imagination, but by the diameter of a rocket fairing. Every marvel of engineering, from Hubble to the James Webb, has been an exercise in brilliant, high-stakes origami, designing intricate structures that fold down into a compact package for launch, only to perform a complex and risky unfolding ballet a million miles from any hope of repair. It's a limitation we've learned to work around, but it's a ceiling nonetheless. Building inside an asteroid completely demolishes that ceiling. Think about the scale we're discussing. The largest asteroids are not mere rocks. They are miniature worlds, some spanning hundreds of kilometers across. Even a modestly sized asteroid, perhaps a kilometer in diameter, offers a cavernous interior volume that dwarfs the payload bay of any rocket ever conceived. This isn't about fitting a pre-built telescope into a hole. It's about reimagining the entire construction process. Freed from the constraints of a launch vehicle, we can design a telescope mirror not to be as small as possible, but to be as large as necessary. The potential for scale is almost incomprehensible. The James Webb's mirror at 6.5 meters across was a monumental achievement, but imagine a single, flawless mirror 50 meters across. Or 100, or a vast, segmented array spanning the entire inner cavity of an asteroid, effectively turning the entire body into one giant telescope. The primary metric for a telescope's power is its light-gathering area. Every square meter of mirror captures more of those precious, faint photons from the edge of time. A mirror with 10 times the diameter doesn't just collect 10 times the light. It collects 100 times more because the area increases with the square of the radius. This isn't an incremental improvement, it's a quantum leap. Such immense size translates directly to breathtaking resolution, the ability to distinguish fine detail. The theoretical resolution of a telescope is determined by the wavelength of light it's observing divided by the diameter of its mirror. A larger mirror means a smaller, sharper point of light for each star, allowing us to see not just blurry blobs of distant galaxies, but to resolve individual star clusters within them. For exoplanet science, this resolution is everything. A telescope with a mirror dozens of meters across could directly image a planet orbiting another star, not as a single pixel, but as a tiny disk. We could begin to map its surface, distinguish continents from oceans, and observe weather patterns on a world light years away. The faint, ancient light from the very first stars, currently stretched into the infrared and diluted to near invisibility by the expansion of the universe, would finally be within our grasp to collect and analyze in detail. And the beauty of this approach is that the very material for these colossal structures is already right there, floating around us. Instead of launching thousands of tons of glass, metal, and composite materials from Earth at astronomical cost, we can use the asteroid itself as our quarry. Robotic miners could process its rich deposits of metals like iron, nickel, and cobalt, while its silicate rocks could be refined into the pure glass needed for mirrors. Advanced 3D printing systems operating in the microgravity inside the hollowed-out asteroid could then fabricate the massive mirror segments and the intricate support structures needed to hold them in perfect alignment. We move from a model of launch and deploy to one of find, process, and build. This changes the entire economic and practical equation, transforming a seemingly fantastical project into a plausible, albeit ambitious, endeavor. The size of our ambitions is no longer chained to the size of our rockets. This shift in construction philosophy is perhaps the most transformative aspect of the entire concept. The traditional model of building everything on Earth and launching it into space is not just incredibly expensive, it's fundamentally limiting. Every kilogram of material we boost out of Earth's gravity costs a small fortune in fuel and rocket hardware. But what if we didn't have to bring the building materials with us? What if the construction site was already overflowing with raw resources, just waiting to be used? This is the promise of in-situ resource utilization, or ISRU, and asteroids are the perfect proving ground for this revolutionary approach. Think of a typical carbonaceous chondrite asteroid. These ancient primitive bodies are essentially time capsules from the early solar system, and they are astonishingly rich in the very materials we would need. They contain vast quantities of iron, nickel, and cobalt, metals perfect for constructing the massive support trusses and frameworks for a giant telescope. Their silicate rocks can be processed into ultra-pure glass, the essential ingredient for crafting the telescope's immense mirror. Perhaps most surprisingly, many asteroids are loaded with water ice, locked away in their shadows or bound within clay-like minerals. This water isn't just for drinking, it's a multi-purpose resource of incredible value. It can be split into hydrogen and oxygen to create rocket fuel for maneuvering thrusters, used in life support systems for any future human crews, or serve as a medium for highly efficient cooling systems to keep sensitive infrared detectors at their required cryogenic temperatures. The process of turning these raw materials into a finished observatory would be a symphony of advanced robotics. Autonomous mining drones equipped with drills and crushers would be the first on the scene, extracting ore and ice from the asteroid's interior. These raw materials would then be transported to processing units that could use a variety of techniques, from simple solar-powered smelters for metals to more complex chemical processes to vaporize and redeposit pure silicon and glass. The final and most elegant step would involve massive 3D printers operating in the microgravity environment inside the hollowed-out asteroid. These wouldn't be the desktop printers we know today. They would be industrial-scale additive manufacturing systems, using lasers or microwaves to sinter metal dust into complex girder structures, or meticulously building up mirror surfaces layer by atomically perfect layer. This entire supply chain, from mine to mirror, would exist off-world, creating a self-sustaining industrial base that operates with only minimal guidance from Earth. The advantages of this approach ripple out in every direction. The most obvious is a dramatic reduction in cost and complexity. By launching only the sophisticated, lightweight robotic fabricators and a small initial supply of fuel and spare parts, we avoid the exorbitant expense of launching thousands of tons of raw mass. This makes previously unimaginable projects financially feasible, but even more importantly, it enables a level of ambition that is simply impossible with the launch from Earth model. When your building materials are literally all around you, the design constraints vanish. You are no longer asking, how big can we fold this to fit in a rocket? You are asking, how big do we need to make it to answer the biggest questions in science? This is how we go from meter-scale mirrors to structures measured in hundreds of meters. It transforms the asteroid from a passive shelter into an active, vibrant workshop, a forge and a factory orbiting the sun, dedicated solely to the pursuit of knowledge and capable of building the tools to acquire it on a scale we are only beginning to dream of. Bringing this vision to life requires a workforce unlike any other, one that can operate millions of miles from Earth in total isolation and under conditions that would be utterly hostile to human life. This is not a job for astronauts in suits. It is a task for a new generation of intelligent, resilient machines. The entire endeavor, from initial survey to final calibration, will be orchestrated by a symphony of advanced robotics and artificial intelligence, working together with a level of autonomy we are only just beginning to master here on Earth. The first arrivals at a candidate asteroid would be a fleet of scout drones. These wouldn't be simple remote-controlled cameras. They'd be sophisticated surveyors equipped with LiDAR for high-resolution mapping, ground-penetrating radar to chart the asteroid's internal structure, and spectrometers to analyze its chemical composition in minute detail. They would swarm over the surface and through any natural crevices, building a comprehensive three-dimensional model of the asteroid, a digital twin that engineers would use to plan every subsequent step of the operation. This initial phase is crucial, as choosing the wrong location to excavate or missing a hidden structural fault could jeopardize the entire mission. Once the perfect site is selected, the excavators move in. These would be heavy-duty robotic miners, far more robust than anything we've sent to Mars or the Moon. Operating in microgravity presents a unique set of physical challenges. A traditional bulldozer-style digger would simply push itself away from the surface with every scoop. Instead, these machines would likely use a combination of gripping claws or anchors to secure themselves, employing precise, controlled bursts from their tools to break apart the rock without sending themselves spinning off into space. They would need to be incredibly resilient, designed to operate in clouds of fine, abrasive dust that would quickly clog and destroy conventional machinery. Every aspect of their design, from sealed bearings to dust-resistant optics, would be a lesson in extreme environment engineering. The real magic, however, happens with the assembly bots. Imagine a swarm of smaller, spider-like robots, each equipped with specialized tools and advanced 3D printers. They would take the raw, processed materials from the miners, the refined metals and the purified glassy silicates, and begin the meticulous work of construction. Guided by a shared AI blueprint, these robots would work in perfect coordination. One group might be sintering metallic dust into the massive, lightweight trusses that will form the telescope's support frame. Another group, working with nanometer precision, could be using focused beams of energy to deposit and polish the segments of the primary mirror, layer by atomic layer. There's no room for error here, and no possibility of a human technician stepping in to adjust a misaligned component. The AI overseeing this process must be capable of real-time problem solving, using a network of sensors to monitor its own work, identify deviations from the plan, and instruct the robotic swarm to make corrections on the fly. This represents the pinnacle of what's known as swarm robotics, where a large number of relatively simple robots achieve complex goals through sophisticated coordination, much like a colony of ants building a mound. The delay in communications from Earth, which could be tens of minutes, makes direct remote control impossible. These systems must be truly autonomous, making millions of independent decisions every hour based on their programmed goals and a constantly updated shared understanding of their environment. This isn't just automation, it's the birth of an entirely new kind of industrial ecosystem, one that is self-planning, self-building, and self-correcting, all in the airless, silent void of space. It's a profound merging of astronomical ambition with robotic ingenuity, creating tools that can then build the tools to see further than ever before. So what are we hoping to see with these colossal, asteroid-housed eyes? One of the most profound and tantalizing goals is to peer back in time to a period cosmologists call the cosmic dawn. This wasn't just the birth of the first stars, it was the moment the universe itself woke up from a deep, dark slumber. For hundreds of millions of years after the Big Bang, the cosmos was a vast, featureless expanse of hydrogen and helium gas, utterly dark and silent. There were no stars, no galaxies, no sources of light at all. It was a true cosmic dark age. Then, gradually, gravity began to pull the densest patches of this primordial gas together. These collapsing clouds grew hotter and denser until, finally, they crossed a threshold and ignited, sparking the very first fusion reactions in the universe. That moment when the first star switched on was the beginning of everything we know, the dawn of light itself. Observing this era is the single greatest challenge in modern astronomy, and our current telescopes, for all their power, are simply not up to the task. The light from those first stars and infant galaxies has been traveling towards us for over 13 billion years. The expansion of the universe has stretched that once energetic ultraviolet light into the long, low-energy wavelengths of the far infrared and radio spectrum. By the time it reaches us, that signal is incredibly faint, a whisper of heat against a backdrop of cosmic noise. It's like trying to hear a single, quiet conversation in a massive, roaring stadium. Ground-based telescopes can't see these wavelengths at all because our atmosphere blocks them. And while space telescopes like JWST are designed for infrared, they face their own limitations. Their relatively small size means they can only gather a tiny amount of this faint light, and their own heat emissions, along with interference from our solar system, create a noisy background that can easily drown out the signal we're desperate to detect. This is where the Asteroid Observatory changes the game entirely. Its sheer size is the first and most obvious advantage. A mirror measured in tens or even hundreds of meters across would have a light-gathering area thousands of times greater than anything we have today. It would act like a colossal funnel, scooping up immense quantities of those ancient, redshifted photons over months of uninterrupted observation. But size alone isn't enough. Stability and environment are everything. The incredible gravitational stability of an asteroid at a Lagrange point means the telescope could hold its gaze on a single patch of sky for phenomenally long periods without the slightest jitter or drift, allowing it to build up an exquisitely deep and clear image, photon by precious photon. Furthermore, being buried deep within the rock provides a level of silence that is simply unachievable anywhere else. The asteroid's mass acts as a perfect shield, blocking out the interfering infrared heat from the Sun, Earth, and even the telescope's own electronics, creating a cryogenically cold, pristine viewing environment. This combination of immense size, rock-solid stability, and perfect quiet is what could finally allow us to capture that first glimmer of starlight from the dawn of time. The scientific payoff of such an observation would be nothing less than revolutionary. For the first time, we would be able to study the properties of those very first population 3 stars. Were they behemoths, hundreds of times more massive than our Sun, burning brilliant and blue before exploding in spectacular supernova, or did they form in a different way altogether? Their violent deaths would have seeded the pristine universe with the first heavy elements, the carbon, oxygen, and iron, that would later become the building blocks for planets and life. By watching this process unfold, we would be witnessing our own cosmic ancestry. Furthermore, this era is intimately tied to the mystery of dark matter. We believe the gravitational pull of dark matter halos was responsible for gathering the gas that formed those first stars. Mapping the distribution and formation of these first luminous objects would therefore give us an indirect but incredibly valuable map of the dark matter scaffolding of the early universe, helping us understand the nature of this invisible substance that makes up most of the cosmos mass. Peering into the cosmic dawn isn't just about looking at a historical event. It's about unlocking the fundamental physics that govern the universe's transformation from a simple, smooth soup of particles into the complex, structured, and beautiful cosmos we see today. It is the ultimate origin story, and an asteroid telescope might be the only tool powerful enough to finally read its first chapter. While the cosmic dawn offers a look back at our universe's infancy, these asteroid observatories could also turn their gaze toward a question that feels intensely personal and immediate: are we alone? The search for life beyond Earth has moved from speculation to a rigorous scientific pursuit, with thousands of exoplanets already discovered. But so far, our methods have been indirect. We mostly infer their existence by watching for the slight dimming of a star as a planet transits in front of it, or by measuring the tiny wobble a planet's gravity induces in its host star. These techniques tell us a planet is there, its approximate size and orbit, but they reveal very little about its true nature. It's like knowing someone lives in a house down the street because you see their shadow occasionally pass by a window, but you have no idea what they look like what the air inside smells like, or if they're even home. An asteroid-based telescope with its potentially vast mirror could change this entire field from inference to direct observation. The primary challenge in directly imaging an Earth-like exoplanet is one of contrast. Imagine trying to see a firefly hovering right next to a massive, brilliant spotlight from miles away. The glare from the star completely overwhelms the faint reflected light from the tiny, rocky planet. Our current telescopes simply cannot overcome this incredible difference in brightness, but a telescope with a mirror dozens of meters across, operating from the pristine, vibration-free environment inside an asteroid, could employ a highly advanced coronagraph or a starshade. These are intricate optical systems designed to physically block the starlight itself, creating an artificial eclipse and allowing that faint, precious planetary light to be seen. It's the ultimate exercise in cosmic photography, removing the lens flare to reveal the subject hidden beside it. Once we can see that pinprick of light, the real magic begins. By collecting that light and passing it through a powerful spectrograph, we can split it into its constituent colors, creating a spectrum. This spectrum is a chemical fingerprint. Specific molecules in the planet's atmosphere absorb light at very specific wavelengths, leaving telltale dark lines in the spectrum. The presence of oxygen, especially in combination with methane, would be a powerful biosignature. On Earth, these gases are constantly replenished by life. Without biology, they would react with each other and disappear from the atmosphere. Finding them together on another world would be the strongest indication yet that we are not the only living planet. We could also search for water vapor, ozone, and other markers that paint a picture of a world that is not just habitable in theory, but potentially inhabited in reality. But the possibilities extend even beyond atmospheric chemistry. The sheer resolution of such a massive telescope could allow us to do something that currently resides firmly in the realm of science fiction: resolve surface features. We wouldn't see continents and oceans in sharp detail, but over time, as the planet rotates, we might be able to detect the difference between the reflective properties of a vast ocean and a large continent. We could potentially map the planet's albedo, its reflectivity, and even observe seasonal changes like the growth and retreat of polar ice caps. And if, by some incredible chance, a technologically advanced civilization existed there, we might detect signs that are impossible to explain through natural processes alone. The persistent, artificial glow of city lights on the planet's night side, or unusual industrial pollutants in its atmosphere, would be evidence of not just life but intelligence. This isn't about receiving a radio signal. It's about looking through a telescope and seeing the faint, collective glow of another civilization's nightly activities, a silent testament to a world alive with its own stories and dreams. The implications of such a discovery would ripple through every facet of human society, from science and philosophy to religion and culture. Confirming that life exists elsewhere would fundamentally alter our understanding of biology, suggesting that the emergence of life is not a miraculous fluke but a natural, perhaps even common, process in a universe ripe with the right ingredients. Finding a second genesis of life would mean the universe is, in fact, bio-friendly. And if we were to find evidence of intelligence, it would force a profound re-evaluation of humanity's place in the cosmos. We would have to confront the reality that we are not the universe's sole experiment in consciousness. This knowledge could unite us as a species, shifting our perspective from one of isolated inhabitants of a single planet to members of a wider cosmic community, with all the humility, wonder, and responsibility that would entail. The search for exoplanets is therefore more than an astronomical exercise. It is a quest to understand our own biological and philosophical context, and an asteroid-based telescope could provide the first clear answers. But our cosmic vision is still obscured by a far more fundamental blindness. We can map billions of galaxies and watch the birth of stars, yet we are forced to admit that most of the universe is made of stuff we cannot see. In fact, the atoms that form everything we know, every planet, every star, and every one of us, account for less than 5% of the total mass and energy in the cosmos. The rest is a profound mystery, split into two enigmatic forces we've named dark matter and dark energy. Dark matter is the invisible gravitational glue that holds galaxies together, while dark energy is the mysterious repulsive force causing the entire universe to expand at an accelerating rate. We know they exist because of their overwhelming effects on the cosmos, but we have no idea what they actually are. They are the two largest pieces of the cosmic puzzle, and they are completely missing. This is where the unique capabilities of an asteroid observatory could become our most powerful tool for discovery. To study these invisible forces, we cannot look at them directly. We must instead observe how they bend and shape the visible universe around them. One of the most promising techniques is called gravitational lensing. According to Einstein's theory of general relativity, massive objects warp the fabric of space-time itself. When light from a distant galaxy travels through this warped space on its way to us, its path is bent, much like light passing through a lens. This means the image of the background galaxy can be distorted, stretched into arcs, or even multiplied. By meticulously measuring these tiny, subtle distortions, astronomers can effectively map the distribution of the matter that caused the lensing effect. The majority of that matter is dark matter. Doing this with the precision needed to crack the mystery requires two things our asteroid telescope provides in abundance: immense resolution and flawless stability. To detect the faint warping caused by a dark matter halo, you need to measure the shapes of millions of incredibly distant, incredibly faint galaxies with micrometer-level accuracy. Any jitter, any vibration, any thermal expansion in the telescope itself would introduce errors far larger than the signal you're trying to detect. The rock-solid stability of an asteroid-anchored platform, holding its gaze for years on end, eliminates that problem. Furthermore, the massive light-gathering power of a huge mirror allows it to see these background galaxies in unprecedented numbers and clarity, providing a rich statistical sample to build a high-fidelity map of the dark matter web that weaves through the entire cosmos. It would be like moving from a blurry, low-resolution sonar image of the ocean floor to a crystal-clear, high-definition map, revealing every trench and mountain range for the first time. The other half of the mystery, dark energy, requires a different but equally precise measurement, tracking the expansion rate of the universe over billions of years. We do this by using certain types of supernova as standard candles, objects whose intrinsic brightness we know, allowing us to calculate their distance by how dim they appear. By measuring both their distance and how much their light has been redshifted by the expansion of space, we can chart how the universe's expansion rate has changed over cosmic history. The discovery that this expansion is accelerating, driven by dark energy, was a Nobel Prize-winning shock that completely overturned our understanding of cosmic evolution. To truly understand dark energy, we need to measure these supernova and millions of other distant objects with even greater precision across a wider span of the universe's history. This again demands a telescope of phenomenal stability and sensitivity. The long, uninterrupted observing runs possible from a Lagrange point allow for the continuous monitoring of distant galaxies to catch these rare supernova events the moment they happen. The vast mirror ensures we can collect enough of their fading light to get a pristine, noise-free measurement of their brightness and spectrum, even from the very edge of the observable universe. This data could reveal whether dark energy is a constant force, as Einstein's cosmological constant suggests, or something more dynamic and strange, which would point toward entirely new physics. An asteroid-based observatory wouldn't just be giving us a clearer picture of the universe we know. It would be providing the data that could finally illuminate the 95% of reality that has, until now, existed only in the shadows of our equations. Even the deepest reaches of space are not the perfect silent darkness we might imagine. For an astronomer, the cosmic environment is filled with a cacophony of interference that can easily drown out the faintest signals from the edge of the universe. Our own planet is a brilliant beacon of reflected sunlight and a blaring transmitter of radio waves from countless communications. The sun itself floods the inner solar system with intense light and a constant stream of charged particles. And in recent years, a new form of pollution has emerged: the growing constellations of satellites orbiting Earth. These thousands of objects, with their shiny metallic surfaces and active transmissions, create a web of moving bright spots and radio chatter that can streakingly ruin long-exposure images and contaminate sensitive data. For telescopes trying to detect the most elusive phenomena, this is the equivalent of trying to hear a pin drop in the middle of a roaring heavy metal concert. An asteroid-based observatory offers a radical escape from this modern cosmic noise. By positioning the telescope far from Earth, perhaps at a stable Lagrange point on the far side of the Moon, or even further out in the solar system, we immediately place a vast buffer of empty space between our instruments and the primary sources of interference. The Earth and its bustling shell of satellites would shrink to a distant, manageable point of light, their polluting effects dramatically reduced, but the asteroid itself provides the second, and perhaps more ingenious, layer of protection. Its solid, rocky body acts as a natural baffle. By orienting the telescope within its excavated cavity to look out through a carefully engineered opening, the entire mass of the asteroid blocks all stray light and radiation from the opposite direction. Imagine it as a photographer's lens hood, but on a colossal, planetary scale. This ensures that only the light from the specific patch of sky being studied enters the instrument, while everything else is cast into shadow. This pristine environment is absolutely essential for the next generation of astronomical studies. Consider the hunt for the first galaxies. Their light is not just incredibly faint, it exists in a very specific, redshifted part of the spectrum. To detect it, telescopes must be exquisitely sensitive to these precise wavelengths. Any stray light at nearby wavelengths, even minuscule amounts, can create a background glow that completely obscures the target signal. The absolute darkness within an asteroid provides the purest possible darkness against which to see these cosmic ghosts. Similarly, for radio astronomers listening to the faint whispers of hydrogen from the early universe or the subtle signatures of complex molecules in distant nebulae, radio frequency interference is a constant enemy. The remote location and the asteroid's rock shield combine to create a radio quiet zone unparalleled anywhere near Earth, allowing for the cleanest data collection imaginable. The difference this makes is not merely incremental, it is transformative. It elevates the quality of observation from a compromised, filtered view to a crystal-clear window. Data that once required complex algorithms to subtract out noise and interference would now arrive in a much purer form, saving immense processing time and, more importantly, eliminating the uncertainties that come with any cleaning process. This level of clarity reduces the margin for error to an unprecedented degree, giving astronomers confidence that what they are seeing is a true feature of the cosmos and not an artifact of their own contaminated environment. It's the ultimate upgrade, moving the entire field of astronomy from a noisy urban balcony to the most remote and silent mountaintop observatory conceivable. Only this mountain is drifting in the profound silence between the planets, offering a view of the universe in its most natural, undisturbed state. This ability to maintain a perfectly stable thermal environment is not just a minor convenience, it is an absolute game-changer for one of the most important and challenging fields of astronomy, infrared observation. To understand why, we need to think about what telescopes are actually detecting. They aren't just capturing pictures of light, they are incredibly sensitive thermometers, measuring the faintest whispers of heat energy from across the cosmos. Now, imagine trying to measure the heat coming from a single candle flame from a mile away, but you're doing it while standing right next to a blazing bonfire. That is essentially the challenge faced by infrared telescopes. Their own heat, and the heat from their surroundings, creates a blinding background glare that can completely overwhelm the faint cosmic signals they are built to detect. This is why missions like the James Webb Space Telescope require such incredibly complex and massive sun shields and rely on a limited supply of cryogenic coolant to keep its instruments just a few degrees above absolute zero. It is a constant, energy-intensive battle against the thermal environment of space itself. An asteroid, by its very nature, offers a profoundly elegant solution to this problem. Think of a large rock sitting in the sun here on Earth. The surface might get very hot, but just a few feet underground, the temperature remains remarkably constant and cool. This is due to thermal inertia. The mass of the rock absorbs heat very slowly and releases it equally slowly, acting as a giant thermal buffer against external temperature swings. Now translate that to the vacuum of space. The sun-facing side of an asteroid might be scorching hot, while the shaded side is brutally cold. But deep within its heart, shielded by meters of solid rock, the temperature is incredibly stable. By placing our telescope in that buried chamber, we are effectively placing it in the most naturally thermostable environment possible in the entire solar system. The wild fluctuations between blistering sunlight and deep shadow that plague free-flying satellites are smoothed out into a near-perfect constant by the asteroid's immense mass. This passive thermal stability is a free gift from physics. It requires no moving parts, no expendable coolants, and no electrical power to maintain. The advantages of this are monumental. First, it dramatically extends the operational life of the instruments. Without the constant thermal stress of expansion and contraction, delicate optical alignments stay perfect for decades, and sensitive electronics are spared the wear and tear that leads to failure. Second, and most importantly, it provides that cryogenically cold environment essential for infrared astronomy by default. While some active cooling might still be needed to reach the absolute coldest temperatures, the massive energy requirements are slashed because the asteroid is already doing 90% of the work. This means the telescope can operate its infrared detectors at peak sensitivity for far longer, potentially for centuries, rather than being limited by the few years' worth of coolant it could carry from Earth. This opens up whole new realms of observation. Consider the study of protoplanetary disks, the swirling clouds of gas and dust around young stars where planets are beginning to form. This process is shrouded in dust that absorbs the star's visible light and re-radiates it as heat in the infrared. To see the birth of planets, to map the gaps and rings where infant worlds are coalescing, we need an infrared eye that is exquisitely cold and stable. Or ponder the hunt for the coolest stars, brown dwarfs, which are failed stars so dim they radiate primarily in the infrared. Their faint thermal signatures are utterly impossible to distinguish from the heat glow of a warm telescope. But with an observatory chilled by the deep, constant cold of an asteroid, these once invisible objects snap into sharp focus, revealing a population of stellar neighbors we never knew were there. This isn't just an improvement in technology, it's the removal of a fundamental barrier that has blinded us to the cooler, hidden half of the universe. Now, when we first hear about the idea of hollowing out an asteroid to build a colossal observatory, our immediate reaction might be to think about the staggering price tag. It sounds like the most expensive science project imaginable, but this is where we need to shift our perspective from a traditional launch model to a new economic paradigm for space exploration. The initial investment would undoubtedly be enormous, likely requiring a global consortium of nations and private entities to fund. However, when we compare it to the long-term costs of the current way we do space-based astronomy, the economic argument starts to look surprisingly compelling. Consider the alternative. The James Webb Space Telescope had a total development and launch cost of around $10 billion. For that, we got a single, phenomenally complex observatory with a finite operational lifespan, ultimately limited by its fuel supply and the inevitable degradation of its components in the harsh space environment. Every time we want to build a new, more powerful telescope, we are essentially starting from scratch, designing a new folding masterpiece, and paying for another incredibly expensive rocket launch. It's a cycle of building disposable, billion-dollar masterpieces. An asteroid-based observatory, by contrast, represents a permanent capital investment in space infrastructure. The upfront cost is for establishing a self-sustaining industrial and scientific outpost. Once the initial robotic fabricators, miners, and power systems are in place, the ongoing costs plummet because you are no longer launching every single gram of material from Earth. The savings come from several revolutionary angles. First, and most significantly, is the drastic reduction in launch mass. Instead of launching a fully assembled telescope, you are launching a much smaller, lighter payload of advanced robotic fabricators, 3D printers, and an initial seed package of specialized components that can't be easily made from asteroid material. This is the difference between shipping a fully constructed house across the ocean versus shipping a toolkit, a set of blueprints, and a single skilled carpenter to a forest where there's an unlimited supply of free lumber. The cost of launching that toolkit is a tiny fraction of the cost of launching the entire house. Reusable rockets from companies like SpaceX are already driving launch costs down by an order of magnitude, making this initial delivery far more feasible. Second, the use of in-situ resources turns a major expense into a free asset. The asteroid itself provides the thousands of tons of raw materials, metals, silicates, and water that would have been prohibitively expensive to lift out of Earth's gravity well. This isn't just a minor saving, it fundamentally changes the economic equation of large-scale construction in space. Furthermore, the water ice found on many asteroids can be processed into hydrogen and oxygen, the primary components of rocket fuel. This means the outpost could potentially refuel spacecraft, creating a celestial gas station that could service other missions to the outer solar system, adding a potential revenue stream, or at least further reducing the costs of supporting the observatory itself. This endeavor will almost certainly be a partnership between international space agencies and private industry. NASA, ESA, and other agencies could provide the long-term scientific vision and initial funding, while private companies specializing in asteroid mining, robotics, and construction could compete to develop the most efficient and cost-effective technologies. This public-private model has already proven successful with the commercial crew and cargo programs that now service the International Space Station. Over time, the goal would be to make these observatories modular and scalable. You wouldn't build one giant telescope and stop. You would start with a smaller proof-of-concept instrument. As the robotic construction systems prove themselves and become more efficient, you could add more mirror segments, expanding the telescope's power incrementally. You could even build multiple specialized telescopes within the same asteroid or across a network of asteroids, each designed for a different wavelength of light or a specific scientific goal. This transforms astronomy from a series of discrete, exorbitantly expensive missions into a continuous, sustainable process of expansion and discovery. It moves us from a model of exploration based on disposable missions to one based on permanent infrastructure. The initial outlay is an investment in a future where the cost of doing big science in space decreases over time because we've finally learned to stop bringing everything with us from home and have started to live off the land, using the abundant resources our solar system has already provided. Of course, the vision of an asteroid observatory is dazzling, but we must also temper that excitement with a clear-eyed look at the formidable obstacles standing between this concept and reality. The engineering challenges alone are staggering, beginning with the very act of excavation. The microgravity environment of an asteroid is a world apart from mining on Earth. There's no stable ground to brace against. A traditional drill would simply spin the entire mining robot uncontrollably in the opposite direction. Engineers are exploring ingenious solutions, like robotic anchors that grip the surface or systems that use the asteroid's own weak gravity to their advantage. But every scoop and every cut introduces complex forces that must be carefully calculated and countered. Then there's the ever-present danger of structural collapse. Asteroids are not solid, monolithic chunks of rock. Many are best described as rubble piles, loose collections of boulders, gravel, and dust held together by their own meager gravity. Hollowing one out without triggering a catastrophic chain reaction that could destabilize the entire body is a delicate, high-stakes engineering puzzle. And the dust, the fine, abrasive regolith that covers these bodies, is a pervasive menace. It could clog moving parts, coat and scratch delicate optical surfaces, and interfere with sensors, requiring robots to be designed with a level of resilience and sealing that far exceeds anything we've sent to the Moon or Mars. These robotic systems themselves represent another layer of immense challenge. They will need to operate with a degree of autonomy that borders on self-awareness. The communication delay between Earth and an asteroid could be tens of minutes, making real-time remote control impossible. Every robot, from the smallest surveyor drone to the largest excavator, must be capable of perceiving its environment, diagnosing problems, and making critical decisions entirely on its own. A jammed drill or a misplaced anchor could spell mission failure if the machine cannot troubleshoot and recover without waiting hours for instructions from a human controller millions of miles away. This demands not just advanced artificial intelligence, but incredibly robust and fault-tolerant hardware that can endure years of continuous, unattended operation in the most unforgiving environment imaginable. Beyond the immediate technical hurdles, we must also confront broader planetary protection and ethical concerns. There is a very real risk of forward contamination, the accidental introduction of earthly microbes to the pristine asteroid. While the goal is excavation, we have a responsibility to ensure we don't compromise these ancient time capsules with our own biological signature, which could ruin future scientific studies of the solar system's organic history. Perhaps even more alarming is the possibility of inadvertently altering the asteroid's orbit. While the change from mining would be minuscule, any miscalculation in the complex gravitational dynamics of the solar system could, over very long periods, theoretically nudge an asteroid onto a less desirable path. The probability might be infinitesimally small, but the potential consequence is so great that it demands rigorous modeling and extreme caution. Finally, this endeavor pushes us into uncharted legal and diplomatic territory. The Outer Space Treaty of 1967 prohibits nations from claiming sovereignty over celestial bodies, but it is far less clear on the rights to use and extract resources from them. Who owns the materials mined from an asteroid? Can a company or nation claim exclusive rights to the resources they extract, even if they can't claim the asteroid itself? How do we prevent a chaotic land rush that prioritizes commercial profit over scientific discovery? Establishing a fair and workable international framework for resource rights, safety protocols, and environmental stewardship in space will be as crucial as solving the engineering problems. Success will therefore depend not only on our technological brilliance, but also on our ability to foster unprecedented global cooperation, ensuring that this new chapter of exploration benefits all of humanity and is conducted with the wisdom and foresight it demands. This concept of building within celestial bodies isn't a sudden flash of inspiration. It's the culmination of a long, rich history of scientific and imaginative thought. For generations, visionaries have looked at the moon and seen more than a cratered companion. They've seen a foundation. The idea of lunar bases, particularly those built within naturally occurring lava tubes, has been a serious proposal for decades. These immense underground tunnels, formed by ancient volcanic activity, offer ready-made shelters from radiation, micrometeorites, and extreme temperature swings, providing a blueprint for how we might use natural planetary architecture to our advantage. It's a short mental leap from a shielded lunar base to a shielded asteroid observatory, applying the same core principle of using what the solar system has already provided. Science fiction has, as it so often does, provided the cultural fuel for these ideas, painting vivid pictures of a future lived within asteroids. The classic image of a hollowed-out space rock serving as a hidden rebel base or a bustling commercial port is a staple of the genre. More ambitious concepts like Gerard K. O'Neill's detailed designs for massive rotating space habitats, the so-called O'Neill cylinders, further explored the notion of creating self-sustaining human environments entirely from scratch in space. These generation ships and orbital colonies, meant to house thousands of people for centuries, required a scale of construction and resource utilization that directly points toward the asteroid belt as the most logical quarry for materials. The fictional narratives gave us the dream, while the scientific proposals from thinkers like O'Neill gave us a plausible, if distant, engineering roadmap. What separates today's discussion from the speculative musings of the past is a powerful convergence of technologies that are turning science fiction into tangible mission plans. The dream of an asteroid observatory is no longer stranded in the realm of what if, because the tools to make it happen are rapidly maturing in the here and now. Advanced robotics capable of autonomous operation in unpredictable environments are being tested on Earth in mines and on other planets with rovers. Additive manufacturing, or 3D printing, has evolved from creating small plastic prototypes to constructing major metal components for jet engines and even experimental habitats, proving it can work in the demanding conditions of space. Most crucially, the skyrocketing frequency of rocket launches and the dramatic reduction in cost driven by private companies are fundamentally changing the economics of space access. We are no longer in an era where a mission to an asteroid is a once-in-a-generation event. It is becoming a realistic, schedulable objective. This journey from imaginative spark to executable plan is a profound testament to human ingenuity. It demonstrates our unique ability to first envision a future that seems impossible, then systematically break down the barriers to making it real. We are a species that looks at a drifting, barren rock and doesn't just see a potential hazard. We see a blank canvas, a foundation, a fortress, and a gateway to the stars. This project represents the very essence of exploration, pushing the boundaries of what we believe is possible by building directly upon decades of speculation, calculation, and unwavering curiosity. The sheer scale and ambition of building an observatory inside an asteroid means that no single nation, no matter how technologically advanced or wealthy, could realistically undertake this endeavor alone. The costs are too high, the required expertise too broad, and the location itself, the common heritage of space, demands a collective approach. This project will almost certainly become the largest and most complex international scientific collaboration in history, a true test of our ability to unite behind a shared goal of discovery. It pushes us beyond the model of a single space agency leading a mission. It necessitates a global consortium where nations contribute not just funding, but their unique technological specialties, their scientific brilliance, and their logistical capabilities, creating a whole that is far greater than the sum of its parts. This new reality immediately bumps up against a legal framework that was established in a very different era. The foundational document for space law, the 1967 Outer Space Treaty, was crafted during the Cold War, with its primary goal being to prevent the militarization of space and the claiming of celestial bodies by sovereign nations. It declares that space is the province of all mankind, and that no nation can claim ownership of the moon or other celestial bodies by means of use, occupation, or any other means. This was a visionary and peaceful principle for its time, but it leaves critical questions about asteroid-based projects frustratingly unanswered. If a multinational consortium spends hundreds of billions of dollars to survey, excavate, and build inside a specific asteroid, do they own the resources they extract? Do they have exclusive rights to operate their facility there, even if they don't claim sovereignty over the asteroid itself? The current treaty is murky on these points, and this legal ambiguity is a significant barrier to attracting the necessary long-term investment. Updating these agreements to create clear, fair, and workable rules for resource utilization and operation rights will be an essential diplomatic prelude to any physical construction, ensuring that activities in space are conducted peacefully, responsibly, and for the benefit of all humanity. We already have powerful blueprints for how this kind of international partnership can succeed brilliantly. The International Space Station stands as a towering testament to what is possible when nations choose cooperation over competition. A project involving the United States, Russia, Japan, Canada, and the European Space Agency, the ISS has operated continuously for over 2 decades, with astronauts and co-scientists from around the world working side by side in pursuit of common goals. It proved that we can manage immense technical complexity and long-term funding cycles through international agreements. On a different scale, the Event Horizon Telescope project demonstrated how global scientific collaboration can achieve the impossible. This was not a single instrument, but a network of radio telescopes scattered across the globe, from Hawaii to the South Pole to Spain. By synchronizing their observations with atomic clocks, they effectively created a virtual telescope the size of Earth itself, an effort that required unprecedented levels of coordination and data sharing between independent observatories and nations to produce the first ever image of a black hole. An asteroid observatory would combine the enduring structural partnership of the ISS with the intense scientific data sharing ethos of the EHT, creating a new model for mega-scale global science. Beyond the bricks and mortar and the legal documents, the most profound product of this collaboration might be the framework for open science that it establishes. From the outset, the mission would need clear, binding protocols for how the incredible torrent of data it generates is handled. Will it be immediately available to astronomers everywhere, or will the consortium members have an exclusive period to analyze it? How do we ensure that scientists in developing nations, who may not have been able to contribute financially or technologically to the construction, still have equitable access to the discoveries? Establishing these guidelines for peaceful use and transparent data sharing from the beginning will be crucial to maintaining global trust and ensuring the project truly serves as a tool for all of humankind, preventing it from becoming a source of geopolitical tension. This endeavor is far more than a technical challenge. It is a diplomatic and philosophical one. It asks us to look beyond terrestrial borders and see ourselves as a single species, building something together that no one of us could build alone, and in doing so, taking a united step forward in our quest to understand our place in the cosmos. So when could we actually see this incredible vision start to take shape? The journey from a whiteboard concept to a fully operational asteroid observatory isn't a single giant leap, but a deliberate, step-by-step march across the remainder of this century. The first phase, which could realistically begin within the next 2 or 3 decades, is all about reconnaissance. We're not sending construction crews, we're sending robotic scouts. These wouldn't be the large, complex miners of the future, but smaller, highly specialized probes designed for a single critical mission to find the perfect rock. They would embark on a grand tour of near-Earth asteroids, conducting incredibly detailed surveys. Their suite of instruments would map surface features with centimeter-level precision, use radar to peer deep into the interior to determine if an asteroid is a solid chunk of metal or a loosely held-together rubble pile, and perform spectroscopic analysis to inventory its precise chemical composition. This isn't just about finding any asteroid, it's about finding the right one, a stable, resource-rich body with the structural integrity to be safely hollowed out. This initial survey phase is the essential foundation, and it's something we already have the technology to start planning today. Building on the data from these scouts, the middle of the century, around the 2050s or 2060s, would likely see the next major milestone, the first small-scale demonstrations of in-situ excavation and fabrication. This is where the theory gets proven in practice. A follow-up mission would land a single, advanced robotic miner and a compact 3D printer on a pre-selected asteroid. The goal here isn't to build a full observatory, but to achieve a series of critical firsts. The first successful extraction of metal ore from asteroid rock in microgravity. The first demonstration of processing that ore into a usable high-grade metal powder. The first 3D printing of a simple, small-scale test structure, perhaps a single beam or a small panel, using nothing but asteroid material. These demonstrations are the crucial baby steps. They will be messy, they will encounter unforeseen problems, and they will provide the invaluable real-world data needed to refine the technologies and scale them up. Success here would be a silent, monumental achievement, broadcast not with a spectacular launch, but with a data packet confirming that a small, perfectly formed truss, made from alien metal, now sits on the surface of an asteroid millions of miles away. The full realization, a sprawling operational observatory with a mirror dozens of meters across, is a project for the latter part of the 21st century. This timeline might seem distant, but it's perfectly aligned with other major goals in space exploration. The development of asteroid mining for water and precious metals will provide the necessary propulsion and life support technology. The push to establish a sustained human presence on Mars will drive advances in the same autonomous robotics and closed-loop systems required for such a distant construction project. Each of these endeavors feeds into and supports the others, creating a rising tide of capability that lifts all boats. The path isn't a straight line, it's a convergent one, where progress in one field accelerates progress in another. The first asteroid observatory won't appear out of nowhere. It will be the culmination of 100 smaller technological victories, each one building on the last, gradually transforming a breathtakingly bold idea into an inevitable and utterly revolutionary feature of our future in the cosmos. To grasp the true impact of these asteroid observatories, we must look beyond the incredible engineering and see them for what they truly are, not just new tools, but entirely new senses for humanity. They promise to revolutionize our understanding of astrophysics and cosmology by finally allowing us to observe the universe in ways that were previously the sole domain of theoretical equations and supercomputer simulations. This is about moving from inference to direct observation, from blurry glimpses into a crystal-clear view of the cosmic machinery at work. Consider one of the most profound and persistent debates in modern cosmology, the theory of cosmic inflation. This idea proposes that in the first fraction of a second after the Big Bang, the universe underwent a period of exponentially rapid expansion, smoothing it out and planting the seeds for all future structure. While inflation elegantly explains many features we see, such as the overall uniformity of the cosmic microwave background, it remains a theory. Different models of inflation make different predictions about the primordial gravitational waves ripples in the fabric of space-time that this violent expansion should have generated. Our current observatories can only barely constrain these possibilities. An asteroid-based telescope, with its unmatched stability and sensitivity, could detect the faint imprint these primordial waves left on the polarization of the cosmic microwave background. It wouldn't just confirm that inflation happened, it would tell us which kind of inflation occurred, effectively allowing us to peer back into the first moments of existence and determine the precise physics that set the entire cosmic story in motion. This would be like finally finding the opening page of the universe's history book, a page we've only ever been able to speculate about. The revelations continue with the enigmatic nature of black holes. Our current understanding is a patchwork of brilliant theory and indirect observation. We've seen the shadow of a black hole with the Event Horizon Telescope and detected the gravitational waves from their collisions with LIGO and Virgo. But an observatory free from atmospheric distortion and armed with a mirror dozens of meters across could directly image the chaotic regions around the supermassive black holes at the centers of galaxies with unprecedented detail. We could watch in real time as gas and dust are funneled into the accretion disk, heated to incredible temperatures and sometimes ejected in powerful jets. This wouldn't be a static image, it would be a dynamic movie of extreme physics, allowing us to test general relativity in its most violent regime. We might finally understand the mysterious connection between a black hole's feeding habits and the evolution of its entire host galaxy, solving a puzzle that has intrigued astronomers for decades. Furthermore, these observatories would do more than just see, they would listen and feel. By working in concert with gravitational wave detectors, an asteroid-based telescope could be the key to multi-messenger astronomy on a grand scale. When LIGO detects a ripple from a neutron star collision, it can only provide a rough sky location. A massive optical telescope, with the ability to rapidly slew and stare with perfect stability, could pinpoint the faint, fleeting glow of the resulting kilonova explosion almost instantly. This precise coordination allows us to study the event in every possible way through gravity, light, and potentially even neutrinos, giving us a complete picture of how heavy elements like gold and platinum are forged in these cosmic cataclysms. It transforms a single signal into a symphony of data. This is the true paradigm shift. It's not merely about better data, it's about accessing entirely new types of information. Just as Galileo's first telescope didn't just make the stars slightly brighter, but revealed moons around Jupiter and the phases of Venus facts that shattered an Earth-centered universe, asteroid observatories have the potential to reveal cosmic truths that will force us to rewrite our textbooks. They could uncover phenomena we haven't even dreamed of yet, perhaps evidence for extra dimensions, new types of particles, or entirely unknown forces that operate on cosmic scales. This endeavor is the next logical step in a journey that began over 400 years ago, a journey of building ever better windows to the cosmos. With these new eyes, we won't just be looking further into space, we'll be looking deeper into the very nature of reality itself, ready for whatever wonders and revolutions that view may bring. Perhaps one of the most exciting aspects of this endeavor is how the monumental engineering challenges of building in an asteroid will inevitably spin off a wealth of new technologies with profound and immediate benefits right here on Earth. This phenomenon, often called the technology dividend, has been a consistent hallmark of ambitious space projects. The Apollo program, for instance, gave us everything from cordless power tools and advanced water filtration systems to the integrated circuit that ultimately made modern computing possible. The quest to construct an observatory inside a space rock will trigger a similar wave of innovation, pushing the boundaries of robotics, materials science, and remote management in ways that will ripple through our terrestrial industries. Consider the advanced robotics required for this mission. The autonomous mining drones and spider-like assembly bots needed to operate with such precision in a low-gravity, high-risk environment represent a quantum leap beyond anything we use today. These won't be remote-controlled machines with a human joystick operator. They will be intelligent, resilient systems capable of perceiving a chaotic, unstructured environment, diagnosing problems, and making critical decisions entirely on their own. The artificial intelligence guiding them will need a level of situational awareness and problem-solving ability that borders on true machine cognition. The spin-offs from developing this technology could revolutionize dangerous or inaccessible jobs on our own planet. Imagine autonomous rescue robots that can navigate the unstable, debris-filled rubble of a collapsed mine or a building after an earthquake, using advanced sensors to locate survivors without risking human first responders. Or consider robotic systems that can perform deep-sea maintenance on underwater oil rigs or communication cables, working tirelessly at crushing depths where humans cannot safely go. The same principles of operating in a hostile, remote environment apply directly, turning a tool for cosmic construction into a life-saving technology for disaster response and high-risk industrial work. The drive for in-situ resource utilization will also force breakthroughs in material science and fabrication. To efficiently process raw asteroid ore into pure metals and high-quality glass in space, we will need to develop entirely new, highly efficient, and compact extraction methods. These might include novel chemical processes that use minimal energy or advanced electrostatic techniques to separate materials in microgravity. The alloys and composites we learn to create from these space-derived resources will be engineered for extreme performance, likely leading to new classes of materials that are stronger, lighter, or possess entirely new properties. These discoveries could filter down to Earth, leading to better building materials for everything from earthquake-resistant skyscrapers to lighter and more fuel-efficient cars and airplanes. The 3D printing technologies perfected for building a telescope mirror segment by segment in a vacuum could be adapted to print entire emergency housing units on site after a natural disaster using local soil and rubble, or to manufacture complex spare parts for critical machinery in remote villages that lack traditional supply chains. Even the software and operational frameworks developed to manage such an incredibly complex, delayed communication project will have enormous terrestrial benefits. Coordinating a swarm of autonomous robots millions of miles away, where a command takes minutes to arrive, requires a revolutionary approach to project management. We will need to create sophisticated simulation software that can predict outcomes with incredible accuracy and develop new protocols for decentralized decision-making and fault tolerance. These complex logistical and planning tools could be adapted to manage large-scale infrastructure projects on Earth, optimize global shipping networks to reduce fuel consumption, or even help coordinate international relief efforts during a pandemic or major crisis, where information is imperfect and central control is difficult. The challenge of building in an asteroid isn't just a series of technical puzzles. It's a masterclass in managing immense complexity under extreme constraints, and the lessons learned will make us better at managing complexity here at home. This constant cross-pollination of innovation, where the drive to explore the cosmos directly fuels advancements that improve life on Earth, demonstrates that the investment in knowledge is never a one-way street. It's a cycle of inspiration and application that makes the grand, outward-looking goal of understanding the universe a deeply practical and beneficial pursuit for everyone. Perhaps the most transformative power of an endeavor this grand lies not just in the data it collects, but in its ability to rewrite our relationship with science itself. A project to build a telescope inside an asteroid is a narrative engine, a continuous story of audacious engineering and cosmic discovery that unfolds over decades. Unlike a traditional space mission that culminates in a single, glorious launch and then operates silently in the background, this would be a living, breathing process. We could follow it in real time. Imagine educational programs where students don't just read about astronomy in textbooks, but instead log into a portal to view live feeds from the optical sensors of a mining drone as it lasers its way through primordial rock millions of miles away. They could watch the daily progress of a 3D printer, layer by painstaking layer, constructing a segment of the primary mirror, turning a raw, abstract concept into a tangible, ongoing achievement. This transparency does more than just educate. It builds a profound and lasting connection. By sharing the stumbles along with the triumphs, the engineering problems solved, the unexpected challenges overcome, the project demystifies the scientific process. It shows that science isn't a list of facts in a book, but a gritty, collaborative, and often messy human endeavor. This creates a sense of collective ownership and shared investment that is utterly unique. A person who has watched a robot they've nicknamed begin excavation in their teenage years might, as an adult, see the first image from that completed telescope and feel a personal stake in that discovery. It transforms the public from passive spectators into active participants in the greatest adventure of our species. The tools for this engagement are already at our fingertips. Interactive simulations could allow anyone to pilot a virtual miner across the surface of a digitally recreated asteroid, experiencing the challenges of low-gravity excavation firsthand. Virtual reality experiences could place users inside the cavernous, completed observatory, floating beside the massive mirror as it stares out into the void. Social media platforms could host Q&A sessions with the engineers and scientists solving problems in real time, breaking down the barriers between the experts and the excited public. This constant, open dialogue fosters a culture that values curiosity, critical thinking, and long-term ambition, inspiring the next generation not just to dream of being astronauts, but to become the roboticists, material scientists, and orbital mechanics who will make those dreams a reality. Ultimately, this project becomes more than a scientific instrument. It becomes a global classroom and a universal source of wonder. In a world often focused on immediate concerns and short-term goals, it offers a compelling, long-range vision that unites people across national and cultural boundaries. It reminds us that we are all quite literally made of star stuff, riding together on a pale blue dot through the vastness of space. By turning the abstract quest for knowledge into a shared, visible journey, we reaffirm that exploring the cosmos is one of the most fundamental and unifying activities we can undertake, a timeless pursuit that connects us to our past and charts a course for our collective future. This expansion of our reach into the cosmos comes with a profound and unfamiliar responsibility. We are on the verge of becoming an interplanetary species, and with that transition comes a critical need to develop a code of ethics for how we interact with the space environment. Asteroids are not just inert rocks to be used as we see fit. They are ancient artifacts, pristine time capsules that have been drifting unchanged since the dawn of our solar system over 4.5 billion years ago. Each one is a frozen record of that primordial era, holding clues to the original ingredients that formed the planets and possibly even the organic compounds that led to life itself. To carelessly contaminate one with earthly microbes during the excavation process would be an irreversible act, akin to using a bulldozer at a delicate archaeological dig. It would forever ruin that body for future scientists who might have far more advanced tools to study it, robbing them of the chance to make their own discoveries. This concept of planetary protection is paramount, demanding that we design our robotic miners and fabricators to be meticulously sterilized, perhaps even constructing them in orbit to avoid any contact with Earth's biosphere, ensuring we leave these cosmic libraries as pristine as we found them for the generations of researchers who will follow us. Beyond the risk of biological contamination, we must also grapple with the physical consequences of our actions on a celestial scale. While the idea of accidentally altering an asteroid's orbit might sound like the plot of a disaster movie, the underlying physics warrants serious consideration. The process of mining, even on a small scale, involves moving mass. In the microgravity environment of an asteroid, ejecting material or shifting significant amounts of rock could, in theory, impart a tiny but cumulative thrust on the body itself. Over long timescales, this minute perturbation could be amplified by complex gravitational interactions with planets, potentially altering its path in unpredictable ways. The probability of nudging an asteroid onto a collision course with Earth is infinitesimally small, but the consequence is so astronomically high that it demands rigorous modeling and extreme caution. Our ethical duty extends to ensuring that our quest for knowledge and resources does not inadvertently create a future hazard, mandating that we develop and adhere to strict engineering protocols to monitor and mitigate any orbital changes caused by our activities. This new frontier also forces us to confront a burgeoning tension between the pure pursuit of scientific knowledge and the powerful allure of commercial profit. The same resources that make an asteroid ideal for an observatory, metals, water, silicates, are also incredibly valuable commodities for a growing space economy. Water ice can be sold as propellant for other spacecraft. Precious metals like platinum could be worth trillions. There is a very real danger that in the rush to capitalize on these resources, the primary scientific mission of an asteroid observatory could be compromised or sidelined. An ethical framework must be established from the outset, one that clearly prioritizes the preservation of these unique scientific sites. This might involve creating protected zones, similar to national parks on Earth, where mining and industrial activity are strictly prohibited to safeguard their research value. It means ensuring that data collected by the observatory remains open and accessible to all humanity, not become the proprietary asset of a private corporation. Finding this balance is not about stifling commerce, but about recognizing that some things, like our window into the origins of the universe, hold a value that cannot be measured in dollars and must be protected for the benefit of all. Ultimately, this ethical journey mirrors a larger evolution in our thinking that is already happening here on Earth. For centuries, we saw nature as an infinite resource to be conquered and exploited. Now we are slowly learning the principles of stewardship, understanding that we have a duty to protect and preserve the environment for future generations. The concept of asteroid-based observatories asks us to take that same mindset and expand it to a solar system scale. We are not just visitors to space, and we are not its conquerors. We are becoming its gardeners, its archivists, and its caretakers. How we choose to treat these first few asteroids will set a precedent for millennia to come, establishing a cultural and ethical template for how a spacefaring civilization should interact with the cosmos. It is a test of our maturity as a species, challenging us to prove that we can explore not with a sense of entitlement, but with a sense of profound responsibility, ensuring that the universe we are working so hard to see remains as wild, pristine, and wondrous for those who will look back after us. While other visionary concepts for next-generation observatories certainly have their merits, the asteroid-based approach emerges as a uniquely balanced solution when we stack it up against the alternatives. Consider the idea of a large observatory on the Moon. The lunar surface offers a stable, rocky foundation, and on the far side, permanent darkness and silence from Earth's radio chatter. These are significant advantages. However, the Moon presents a massive logistical hurdle. We have to bring absolutely everything with us. Every kilogram of steel for the structure, every ounce of glass for the mirror, every liter of water and fuel for support systems would need to be launched from Earth at tremendous cost and energy. The Moon's gravity, while only 1/6 of Earth's, is still substantial enough to make landing heavy equipment a complex and risky endeavor. Essentially, building a large lunar telescope means reconstructing our entire industrial supply chain on another world from scratch, a daunting prospect that could delay such projects for generations. Then there's the concept of free-flying swarms, a fleet of smaller, independent telescope modules that would fly in a precise formation to act as one giant virtual instrument. This is a brilliant workaround for the size constraint, and projects like the proposed Starshade with the James Webb Telescope are already exploring this technology. The major vulnerability of this approach, however, is its exposure. Each individual module in the swarm is just as susceptible to radiation, micrometeorite damage, and thermal stress as any other satellite. They would require their own complex propulsion systems to maintain their exact positions relative to each other, constantly burning fuel and introducing points of failure. There's no collective shield protecting them. A single impactful grain of sand could cripple a critical component and degrade the performance of the entire array. It's a powerful idea, but one that inherits all the traditional frailties of space-based hardware. This is where the asteroid concept finds its powerful niche, offering a best of both worlds compromise. Unlike the Moon, an asteroid provides the raw materials for construction on site, turning a logistical burden into a strategic advantage. And unlike the fragile free-flying swarms, the asteroid itself serves as a monolithic, passive shield, a fortress of rock that protects the priceless optics within from the relentless hazards of space. Their locations are also key. Many ideal candidate asteroids reside in stable orbits, like the gravitationally calm Lagrange points, offering that priceless observational stability without the need for constant, fuel-guzzling corrections. They are remote enough to avoid the interference plaguing near-Earth space, yet still within a manageable distance for robotic missions compared to destinations in the outer solar system. This isn't to say we should abandon other ideas. A diversified strategy is the wisest path forward. Small, free-flying telescopes will always be incredible tools for rapid, targeted observations. A lunar observatory, particularly on the far side, would be unparalleled for certain types of radio astronomy. The true power of the Asteroid Observatory lies in its specialization for the most demanding, long-duration missions, those requiring unprecedented size, perfect stability, and absolute silence for years on end to capture the faintest whispers from the edge of time and space. It's not about picking one winner, but about building a robust portfolio of cosmic vantage points, each playing to its unique strengths. For the specific, monumental task of staring into the cosmic dawn or directly imaging an Earth-like exoplanet, the natural combination of resources, protection, and stability offered by an asteroid makes it not just a good option, but potentially the only viable path to achieving what was once thought to be impossible. This shift toward a new space economy is being driven not just by government agencies, but by a burgeoning ecosystem of private companies whose innovations are fundamentally changing what is possible. For decades, the astronomical cost of reaching orbit was the single greatest barrier to ambitious projects. Launching anything into space was a phenomenally expensive, one-and-done proposition, with massive rockets being discarded into the ocean after a single use. This economic reality placed a hard cap on the scale and frequency of missions, forcing scientists to dream small and pack their instruments into ever more ingenious but constrained packages. The entrance of companies like SpaceX and Blue Origin has shattered that old paradigm. Their relentless focus on reusability, landing and reflying rocket boosters is not a minor improvement, it is a revolution. It's the difference between building a new airliner for every single flight and having one that can be refueled and flown again. This single innovation has already slashed the cost per kilogram to orbit by an order of magnitude, and that trend is only continuing downward. This dramatic reduction is the key that unlocks the entire concept of an asteroid observatory, transforming it from a fantastical thought experiment into a project with a conceivable budget. Beyond just providing cheaper taxis to space, these companies are also the primary developers of the heavy lift infrastructure required to get the initial robotic seed ships on their way. SpaceX's Starship vehicle, designed to be fully reusable and capable of carrying over 100 metric tons to orbit, represents the kind of payload capacity needed to deploy the large-scale miners, fabricators, and power systems that would serve as the vanguard for an asteroid mission. It provides the delivery truck, while companies specializing in robotics and in-situ resource utilization, like Astroforge or Planetary Resources, are developing the tools and techniques that would turn the asteroid's raw material into a finished observatory. This division of labor is the essence of the modern public-private partnership model. Instead of a single space agency attempting to master every discipline from rocket science to metallurgy, we see a thriving marketplace of specialization. NASA or the European Space Agency can act as the anchor customer and the source of rigorous scientific requirements, defining the what and the why. Private companies then compete to innovate and provide the most efficient and cost-effective solutions for the how, handling the complex logistics of transportation and construction. This allows the scientists and astronomers to focus on their core mission of discovery, not on the intricacies of rocket propulsion or robotic excavation. This collaborative model effectively blurs the traditional lines between pure exploration and commercial enterprise. The same robotic arm designed to carefully position a telescope mirror segment could, with slight modification, be used to sort mined ore for a separate commercial venture. The advanced autonomous navigation software that guides a survey drone through a dark asteroid cavity could be licensed for use in autonomous vehicles on Earth. A company investing in the technology to build an observatory might also use that expertise to construct communications hubs or fuel depots for other clients, creating a virtuous cycle where advancements in one area fund and inform progress in another. The future of astronomy, therefore, may not depend solely on the brilliance of astronomers with their eyes on the stars, but equally on the vision of entrepreneurs and engineers who are building the industrial foundation to get us there. Their drive for efficiency, scalability, and profit is not at odds with the quest for knowledge. It is becoming the essential engine that will carry it forward, proving that the final frontier can be a place of both profound discovery and sustainable enterprise. History has a wonderful way of humbling our scientific ambitions, reminding us that every time we build a new window to the cosmos, we are greeted not just by the answers we sought, but by questions we never thought to ask. The story of astronomy is filled with these glorious accidents, moments of pure, unexpected discovery that fundamentally reshaped our understanding of reality. When radio astronomers Jocelyn Bell Burnell and Anthony Hewish built a new telescope in the 1960s, they were studying the scintillation of quasars. What they found was a regular, repeating pulse so precise they half-jokingly labeled it LGM for Little Green Men. It turned out not to be a signal from an alien civilization, but the first discovery of a pulsar, a rapidly spinning neutron star, a type of object whose existence was only theoretical until that moment. It was a complete surprise that opened up an entire new field of astrophysics. Similarly, the first confirmation of planets orbiting other stars in the 1990s wasn't the result of a dedicated exoplanet mission. It was an unexpected byproduct of studying pulsars again. These weren't failures of planning. They were the universe rewarding our curiosity with gifts we didn't know to ask for. An observatory of the scale and sensitivity we're discussing, nestled within an asteroid, is practically engineered for surprise. Its core mission is to push into realms of the universe we have never seen before, to observe phenomena that are currently nothing more than lines in a theoretical physicist's notebook. This means we must architect the entire project not just to confirm our existing models, but to be gloriously, productively wrong. The hardware and software must be designed for maximum flexibility. Imagine a telescope that is programmed for a year-long exposure to study the cosmic dawn, but its peripheral sensors detect a bizarre, fleeting flash of energy from an entirely different part of the sky. A flash that doesn't match any known supernova, gamma-ray burst, or human-made satellite. A rigid, single-purpose mission might ignore this anomaly to stay on its pre-programmed task, but a flexible one could have the autonomous intelligence to briefly divert a portion of its immense processing power to capture a high-resolution spectrum of that event while simultaneously alerting other observatories across the globe and in space to turn their eyes toward this new mystery. This requires building in a level of artificial intelligence that isn't just about problem-solving, but about curiosity algorithms that can recognize the statistical signature of the truly anomalous and have the authority to investigate. This philosophy must extend to the data itself. The traditional model in science often involves a proprietary period where the principal investigators who built the instrument have exclusive first access to the data they collect. For a discovery of this potential magnitude, that model is untenable. The data streaming from an asteroid observatory should be part of an unprecedented open data experiment, made available in near real time to a global community of astronomers, physicists, chemists, biologists, and even citizen scientists. The sheer volume and complexity of the information will be so vast that no single team, no matter how brilliant, could possibly analyze every potential signal. The key to deciphering an unexpected discovery might lie in the pattern recognition skills of a machine learning expert in Mumbai, the theoretical framework of a cosmologist in Buenos Aires, or the sharp eyes of an amateur astronomer in Oslo who notices a tiny, weird blip that everyone else's algorithms filtered out as noise. This open-source approach to cosmic discovery turns the entire world into a collaborative lab, dramatically increasing our odds of recognizing a revolution when it appears. And when that revolution comes, it will demand a new kind of scientist, or rather, a new kind of scientific teamwork. The silos that have traditionally separated astronomy from biology, physics from chemistry, will need to dissolve. Suppose the telescope's spectrograph, while analyzing the atmosphere of a distant exoplanet, detects a combination of gases that is not just suggestive of life, but is utterly impossible to explain through any known geological or atmospheric process. Interpreting that signal won't just require an astrophysicist, it will require a biochemist to model alien metabolic processes, a geologist to rule out every conceivable non-biological explanation, and a planetary scientist to understand the world's climate. The discovery of something truly unforeseen, like evidence for a force beyond the standard model of physics or an object that defies our understanding of space and time, would necessitate a similar convergence of disciplines, pulling in particle physicists, string theorists, and philosophers to help make sense of what we're seeing. This is where the final and most human preparation comes into play, the cultivation of humility. We must embark on this journey with the explicit understanding that our most cherished theories are not unshakable truths, but the best models we have based on the limited data we've collected so far. The history of science is a graveyard of elegant, seemingly complete theories that were appended by a single, inconvenient observation. Preparing for the unknown means being emotionally and intellectually ready to let go, to admit that the universe is stranger, more complex, and more wonderful than we had ever imagined. The greatest discovery an asteroid observatory could make might not be a thing, but a realization that we are only just beginning to comprehend the magnificent, bizarre, and breathtaking reality of the cosmos we call home. But the true power of this vision is unlocked when we stop thinking of these observatories as isolated outposts and start seeing them as a single, coordinated instrument, a network. Imagine not just one asteroid telescope, but a dozen or even 100, each strategically positioned across the solar system, nestled within their own carefully chosen celestial bodies. This isn't about redundancy. It's about creating a capability far greater than the sum of its parts. Each observatory in this network could be specialized, its instruments fine-tuned for a specific slice of the electromagnetic spectrum. One might be optimized for the long, faint waves of radio astronomy, listening to the whispers of primordial hydrogen. Another could be dedicated to the high-energy fury of gamma rays, watching for the most violent explosions in the universe. A third might focus exclusively on the infrared, peering through cosmic dust clouds to witness the birth of stars. This division of labor allows for a level of specialization and precision that a single, general-purpose telescope could never achieve, turning each node into a master of its particular cosmic domain. The most breathtaking potential, however, lies in a technique called interferometry. This is where these separate observatories stop working alone and begin to act in perfect concert. By precisely synchronizing their observations using atomic clocks and combining their data, this dispersed network can effectively function as one single, colossal telescope. The theoretical resolution of a telescope is determined by the distance between its components. So, while a single asteroid might host a mirror a kilometer wide, A network of observatories spread across the orbital paths of Mars or Jupiter would create a virtual instrument with a diameter measured in hundreds of millions of kilometers. The resolution this would provide is almost beyond comprehension. We're not just talking about seeing the surfaces of distant exoplanets, we're talking about mapping them. We could distinguish cloud patterns, track weather systems, and potentially even identify signs of surface activity on worlds orbiting other stars. It would allow us to watch matter spiraling into the supermassive black hole at the center of our galaxy, not as a blur, but in stunning, dynamic detail, testing the laws of physics in the most extreme environment imaginable. This distributed architecture also creates a resilient and ever-watchful sentinel system for the cosmos. A single telescope, no matter how advanced, has a limited field of view and is subject to downtime for maintenance or calibration. But a network ensures that the universe is under constant surveillance from multiple angles simultaneously. A brilliant gamma-ray burst, the death cry of a massive star in a galaxy billions of light-years away, would be detected by multiple nodes at once. This multi-angle data is priceless, allowing astrophysicists to triangulate its exact origin and study the event's structure and evolution in 3 dimensions. The same applies to supernova, neutron star collisions, or any other fleeting cosmic event. With a network, we're not just hoping to accidentally catch these transient phenomena, we're guaranteeing that we will, providing a continuous, multi-perspective record of the most dynamic and violent processes in the universe, ensuring that not a single cosmic event goes unobserved. This transforms our entire approach to astronomy from a series of discrete, finite missions into a permanent, evolving infrastructure. It's the difference between building a single, magnificent lighthouse on a distant shore and constructing an entire global network of navigation satellites. One is a brilliant but isolated beacon. The other is a seamless, integrated system that provides constant, reliable coverage for the entire planet. An asteroid observatory network becomes humanity's permanent, unblinking eye on the cosmos, a foundational piece of scientific infrastructure that would serve generations of scientists for centuries to come. It ensures that our view of the universe never goes dark, that our quest for understanding continues uninterrupted, and that we are always ready for the next great discovery, waiting patiently in the depths of space for its moment to reveal itself. Building telescopes inside asteroids represents far more than just an incredible engineering achievement. It signifies a fundamental shift in our relationship with the cosmos itself. For centuries, our approach to astronomy has been defined by a clear separation between the observer and the observed. We built delicate instruments on our planet, or placed them precariously in the void, always struggling against the environment to steal glimpses of the universe. This new vision shatters that old paradigm. Instead of fighting the harsh realities of space, we learn to work with them. Instead of seeing asteroids as obstacles or threats, we recognize them as partners in exploration, offering shelter, resources, and a stable foundation. This is the move from simply looking at the universe to truly learning to live and work within it, integrating our quest for knowledge with the very fabric of the solar system. The discoveries that could flow from such an endeavor are not merely incremental. They have the potential to be genuinely transformative, answering questions that have lingered at the very heart of human curiosity for millennia. Are we alone in the universe? An asteroid-based telescope could give us our first definitive answer by analyzing the atmospheres of distant Earth-like worlds for the unmistakable chemical signatures of life. How did everything begin? By peering back to the cosmic dawn to witness the ignition of the first stars, we would be watching our own cosmic origin story unfold. What is the true nature of reality? dominated by forces we cannot see. By mapping the invisible webs of dark matter and measuring the relentless push of dark energy with unprecedented precision, we could finally illuminate the 95% of the universe that currently exists only in our equations. This isn't just about getting better data, it's about accessing a new tier of understanding, one that could redefine physics, philosophy, and our perception of our place in the grand scheme of existence. Ultimately, this project is a powerful testament to the best of humanity, our boundless curiosity, our ability to innovate through collaboration, and our relentless drive to explore. It requires the marriage of astronomical vision with robotic ingenuity, the partnership of global space agencies with private industry, and the shared will of an entire species to reach for a goal that benefits all of humankind. It proves that when we dare to imagine a future that seems impossible, and then systematically break down the barriers to make it real, there is no limit to what we can achieve. The cosmos is not a static painting to be admired from a distance. It is a dynamic, breathtaking story waiting to be read. And with these new eyes, built within the ancient rocks of our solar system, we are poised to turn the page and begin a thrilling new chapter in that story. The future of discovery isn't just above us, it's all around us, waiting within the drifting mountains of space for us to finally look inward